optical isomerism now. Now, optical isomerism is a form of stereoisomerism. Remember that stereoisomers have the same structural formulae, but a different arrangement of atoms in space. Optical isomerism is a very specific form of stereoisomerism. For optical isomerism to occur, you need 4 different substituents attached to one carbon atom. And remember, we call this central carbon atom a chiral center, or a chiral carbon. The result of this is that you have 2 isomers that are non-superimposable mirror images of one another. And these optical isomers are actually known as enantiomers. So how do we distinguish enantiomers from each other? A very key difference is that they rotate plane polarized light in opposite directions, which means it makes them optically active. An equal mixture of enantiomers is known as a racemic mixture, a racemate. Racemic mixtures have no effect on plane polarized light. We call them optically inactive, and that's because the rotation in opposite directions caused by each enantiomer is cancelled out due to the equal mixture of enantiomers. So how do we recognise chiral carbons and how do we draw optical isomers? We'll go through a variety of examples here. So we can see we have a chiral carbon here. The reason for that is we have 4 different groups attached. The hydroxyl group here, the carboxyl group here, we have C2H5 and CH3. Do notice that when we use the word group, we're not just referring to a single atom next to that central carbon, it's all the preceding atoms until we reach the end of the chain. Here we have a skeletal formula. This actually represents a structure with 2 chiral carbons. I'll highlight them here, 1, 2, because if you double check, you can see that each of these carbons has 4 different groups attached. Remember that we only show hydrogens in a skeletal formula that form part of a functional group, hence why that hydrogen is present here. So we've looked at 2 chiral carbon examples. Now to show you one which isn't a chiral carbon. Now, simply owing to the fact that this molecule is symmetrical, it means it can't have a chiral carbon. I'm going to use my highlighter again here to represent a chiral carbon here. Now, the 4 groups attached are a hydrogen, which again we can't see because of the fact that this is a skeletal formula. We have NH2, and then we have some really large groups of CH2, 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 CHOH, as well as CH2, CHOH. So we've mentioned that optical isomers are non-superimposable mirror images of one another, but how do we draw them? So I'll write a list of instructions here. Step 1 is draw the molecule in 3D, making sure that your chiral carbon is in the center. Your second step is to draw a mirror line. And then to draw the second enantiomer, you want to draw the mirror image of the molecule on the right-hand side. So I'm going to start by drawing my molecule in 3D with my chiral carbon in the center. So there's step 1. Now I'm going to do step 2, which is draw my mirror line as a dotted line. And now I'm going to draw the mirror image of that molecule nice and carefully. So how might you be asked about this in the exam? Well, you could be asked to deduce structures using optical activity. So here we have compounds A and B with this molecular formula. We know that A shows optical activity, B does not. Draw one possible structure for each of the species. So we'll start with A, which we know is optically active, which means it has by definition a chiral carbon with 4 different groups attached. So I'm going to start with my central carbon atom. I know I need to obey this molecular formula. So to explain why this structure here is optically active, we have our central carbon, and then we have 4 different groups attached to that chiral carbon. We can see that we have CH3, hydrogen atom by itself, chlorine by itself, and then lastly CH2Cl. So here is our chiral carbon. It is optically active. And then what about the structure of B, which we know is optically inactive? So we need to arrange these atoms so that we don't have 4 different groups attached to that central carbon. So B is optically inactive. The easiest way to draw that is by drawing that central carbon and then immediately adding 2 identical groups, in this case 2 hydrogen atoms. This renders this structure immediately optically inactive because they are the same group, and then all I've done is make sure I fill up with the rest of the atoms to ensure that the overall molecular formula is correct. It's now time to turn our attention to 2 very closely related homologous series, the aldehydes and ketones. So the functional group of the aldehydes is CHO, CHO, and the functional group of the ketones looks like this. So as it's clear to see here, both contain the carbonyl C double bond O group. How do we go about naming them? We'll start with aldehydes. Aldehydes in most cases end in al. For example, ethanal, propanal. Now, because the aldehyde has to be at the end of a carbon chain, as we see here, there's no need to put a number in when you go about naming them, because the carbon of the aldehyde is assumed to be carbon number 1. How about naming ketones? Well, ketones end in -one. If we take propanone and butanone, so this is propanone due to the fact that you have 3 carbons and the carboxyl group in the middle with 2 R groups attached. What about butanone? Now, because the carbonyl group for both propanone and butanone can only be on 1 possible carbon, a number is not needed here, but as you increase the length of the carbon chain, that's when you start introducing numbers into the naming convention. So for this larger structure, we need numbers to locate the carbonyl group in the chain. So we can see here that we have 5 carbons. The carboxyl group is on the 2nd carbon, so this is pentan-2-one. One thing to be aware of with the aldehydes, a slight change in their naming, is if you have an aldehyde attached to a benzene ring, which I'm drawing right now, this is known as benzene carbaldehyde, and we are using the suffix carbaldehyde as soon as a benzene ring is involved. Let's look at the functional groups again of the aldehydes and ketones to try and understand how these various homologous series are going to react. Now we can see straight away that that carbonyl group is going to be strongly polar. We're going to have a delta positive carbon, a delta negative oxygen. And that means that there are permanent dipole-dipole forces between molecules. So these are stronger, remember, than van der Waals forces, London forces, but weaker than hydrogen bonds. And therefore, we can infer that aldehydes and ketones have a higher boiling point than similarly sized alkanes, but a lower boiling point than alcohols because they don't have hydrogen bonds. Alcohols, remember, are famous for having hydrogen bonds. We've looked previously at the fact that we can easily distinguish between aldehydes and ketones using Fehling's solution or Tollens reagent. This relies on the fact that aldehydes may be oxidized to carboxylic acids and therefore, if you have an aldehyde added to Tollens reagent, you get what's known as a silver mirror. No such reaction occurs with a ketone, And if you prefer, you can mention the failings test, where you'll get a brick red precipitate in the presence of an aldehyde. Watch another video in order to actually see the chemistry behind this, because it is important, particularly with AS chemistry, that you know this. I just wanted to mention it here. So going back to this electron-rich oxygen and the electron-deficient carbon, what this means is that the electron-deficient carbon is readily attacked by reagents which have electron-rich areas, such as negative ions or compounds with lone pair of electrons, which remember we refer to as nucleophiles. So we're going to expect plenty of mechanisms here with aldehydes and ketones which involve nucleophilic addition. So I'm going to run you through the nucleophilic addition reaction using aqueous NaBH4 on, first of all, an aldehyde. So to remind you, here's our aldehyde functional group, meaning that this oxygen is electron rich, this carbon here is electron deficient. Do practice naming this aldehyde when you get the opportunity. 1, 2, 3, 4. We have 4 carbons. We have a methyl group on what is in effect the second carbon. So we have 2-methyl butanol. I'm going to rub that out so we can see what's going to happen in terms of the transfer of electrons. Now, you do need to be aware that the NaBH4 is super unusual, that it produces a hydride ion, H- ion, which has a lone pair of electrons in solution, which is acting as your nucleophile. So this electron-rich nucleophile is going to attack our slightly positive carbon, which causes one of the bonds in the C double bond O to break. So we're using curly arrows to represent that. We now have a lone pair of electrons on our oxygen, which is going to be attracted to an H+ ion. The H+ ion comes from either the solvent used or an acid added. Remember, our curly arrows always go from a lone pair of electrons or a bond. That hydrogen now adds itself as an alcohol functional group, a hydroxyl. And therefore, if we look at what we have here, again, we have 4 carbons in a row. We've got a methyl group, alcohol functional group. So the name of this is 2-methyl butanol. Remember to always look back at what's actually going on overall. So through the nucleophilic addition reaction using our aqueous NaBH4, the one that contains the hydride ion, we have reduced our aldehyde to a primary alcohol. Remember, this is a primary alcohol because the carbon that the alcohol functional group is attached only has 1 carbon adjacent. So overall, our aldehyde has been reduced to a primary alcohol. And if you want to write a summary equation, you can write this instead of the mechanism. There's CHO for our aldehyde. This represents our reducing agent. Let's do a similar mechanism now involving ketones and NaBH4. Again, it's going to be a nucleophilic addition reaction. We're going to be adding our nucleophile. There's our slightly negative oxygen, slightly positive carbon. Don't forget to use the opportunity here to attempt to name this ketone. We have 1, 2, 3, 4 carbons, so it's simply butanone. Now, let's get into our mechanism. So we're starting with our hydride ion with a lone pair of electrons acting as our nucleophile that's going to attack our slightly positive electron deficient carbon. And then very similar to what we did before, that lone pair on the oxygen is going to attack our hydrogen ion that's come from a solvent or the acid which has been added. What do we have here then? We have a alcohol again, but look, this carbon is now attached to 2 carbons, which means it's a secondary alcohol. What is its name? it's butan-2-ol. Do be aware, I know we've already said it's a nucleophilic addition reaction, but it's because the carbon here starts with 3 groups attached, 1, 2, 3, and ends up with 4 groups attached, hence why it's an addition reaction. So to summarise, ketones are reduced to secondary alcohols. If we write the summary equation here, here's our reducing agent, here's our secondary alcohol. And it's important to be aware that we can't reduce either aldehydes or ketones to tertiary alcohols. If you try and draw it out, it will never work. Formation of racemic mixtures from aldehydes and ketones. We're combining everything we've just learnt to do with nucleophilic addition reactions and how optical isomers involve the production of enantiomers, which are non-superimposable mirror images of one another. We're going to show how the products of these nucleophilic addition reactions produce a racemic mixture. So here I have a generic structure of a ketone. As always, we've got our slightly negative oxygen, our slightly positive carbon. I'm going to just use this to represent a nucleophile. I don't really mind which one it is because after all I'm using this to demonstrate how we can form racemic mixtures from aldehydes and ketones. Now what you need to be aware of here is that this carbonyl group is planar, and that means it can be attacked by a nucleophile either above or below. And it's this that creates the racemic mixture. I'm going to use my mirrored line. I'm going to draw my first isomer on the left, my first enantiomer. I'm showing that my nucleophile has added itself. Then I draw my mirror image over here to show my second enantiomer. And because our racemic mixture, remember, contains a 50-50 mixture of these two enantiomers, despite the fact that they rotate plane polarized light in opposite directions, their effects cancel each other out, so we say that the racemic mixture is optically inactive. Okay, so here's our aldehyde to begin with. This is propanol. It's got 3 carbons. Our nucleophile in this case is the cyanide ion. There's the all-important lone pair. Just be aware that we use KCN to produce our cyanide ion instead of another option, which is HCN. And the reason for that is because HCN produces a toxic gas. And the other issue is that HCN is a weak acid, meaning that the concentration of cyanide ions is too low, so the rate of reaction is too slow. So let's get underway then. The lone pair exists on the carbon. It's going to attack the slightly positive carbon here, causing the breakage of that bond. Due to this step here, we're obviously going to add our cyanide ion onto our original substance. The oxygen has gained a lone pair of electrons. So our next step is realizing that the fact that there's a dilute acid here means that we have H+ ions present, which that lone pair is going to attack from the oxygen. So to complete this structure, so in terms of naming this product, due to the presence of the CN here, we have a nitrile. Count your number of carbons, it's 4. Just be a little bit careful here, you need to write butane nitrile here. That E is essential, they will knock off a mark if you don't include it. And then obviously we have the OH here, so that goes at the front according to our IUPAC naming convention. So that's 2-hydroxybutane nitrile. Now, one thing to be aware of here is this is a chiral carbon, and as is the case when aldehydes react in a nucleophilic addition reaction in this way, you actually produce a racemic mixture of enantiomers. I haven't shown all the wedges and dotted lines because it would get way too complicated. But remember, because of that carbonyl group being planar, the nucleophile can attack either above or below, so it will actually provide a racemic mixture containing 2 enantiomers. Let's now take propanone and KCN and dilute acid. Again, that mechanism is going to be nucleophilic addition. Here's our cyanide ion, which attacks that slightly positive carbon, breaking that double bond. Exactly the same as before. The oxygen gains a lone pair and attacks the dilute acid's H+ ion. So we'll end up with a hydroxyl functional group up here. Let's name it. This bit represents nitrile. This is a methyl group on the second carbon. This is a hydroxyl group on the second carbon. So to name, it is 2-hydroxy, 2-methyl, propane, nitrile. And there's that all-important E again. Now, ketones will produce racemates, but propanone won't, and that's because it's a symmetrical ketone. So look, you can see that there. Now, these reactions on the whole are pretty useful, and part of the reason for that is because the carbon chain length is extended due to that carbon in the cyanide ion. Butanone is reduced in a 2-step reaction using NaBH4 followed by dilute hydrochloric acid. Write an overall equation for the reduction of butanone using this to represent the reductant. So we're going to start with a ketone. We know we're going to reduce it to a secondary alcohol as per the contents of my video. Let's write the formula of butanone. It's got 4 carbons. There's that ketone functional group. Here's our reductant. And now we need to write the formula of a secondary alcohol. Feel free to write out the displayed formula if you want to see how that secondary alcohol comes about. By considering the mechanism of the reaction, explain why the product has no effect on plain polarized light. So what I'm going to do here is I'm going to draw the mechanism just to show you really what's going on so we can understand, first of all, that enantiomers are formed, and then we'll go on to explain that despite the fact that those enantiomers are formed, that it has no effect on plain polarized light. So here's butanone. Here's our hydride ion with the lone pair that attacks the electron deficient carbon, breaking that double bond. Here's our oxygen with its lone pair. The lone pair attacks the hydrogen ion from the dilute acid. So here's our product, our secondary alcohol. And sure enough, we have our chiral carbon. We have our central carbon atom, which is surrounded by 4 different groups. So yes, we have 2 enantiomers which can form. And remember, that's due to that carbonyl functional group being planar, meaning that our nucleophile, the hydride ion, can attack either above or below. However, the 2 enantiomers that exist are formed in equal amounts. Remember, we call that a racemic mixture. And therefore, even though they rotate the plane polarized light in opposite direction, the rotation is cancelled out due to the presence of these enantiomers in equal quantities. Here's our full answer then, that will get us our 6 marks. The carbonyl compound, it's an aldehyde, I can see that straight away, reacts very slowly with HCN. Name and outline a mechanism for the reaction of the aldehyde with HCN. This is nucleophilic addition. With propanol. We have our cyanide ion with the lone pair that attacks that electron deficient carbon, breaking the double bond. Our oxygen gains a lone pair, which attacks the hydrogen ions also present. Here's our product. The reaction in part A produces a pair of enantiomers. Draw the structure of each enantiomer to show how they're related to each other. So I am going to start by drawing this in 3D. We add our dotted line to represent the mirror, and then we draw our mirror image super carefully. And as you'd expect to see, of course, because we have enantiomers, we have that chiral carbon with 4 separate groups attached. State and explain how you could distinguish between the 2 enantiomers. Plain polarized light is rotated in opposite directions. Give the IUPAC name of the product of the reaction in part A. So we're naming this. So notice we have the nitrile here that goes at the end. Count the number of carbons. Remember, we've gained an extra carbon, so we now have butane. Because it's a nitrile, we need to include that E. And then finally acknowledge the OH. It's on the second carbon, so we have 2-hydroxy butane nitrile. In practice, KCN rather than HCN is added to the carbonyl compound. Given that the acid dissociation constant for HCN is this, suggests why the reaction with HCN is very slow. So we're going to write that HCN is a weak acid. Remember, weak acids only partially dissociate, so the concentration of HCN in solution is very low. Meaning that therefore, the reaction proceeds at a very slow rate.